Okay, how are we doing? Questions? So there are a number of outstanding comments. Anything that you sent me about runtime.cc, those are pending, but yes, I've seen them. Were you going to ask me about that? No. What are you going to ask me?
The string printing actually works.
Yes? So you're doing something wrong.
So if I'm passing in like a dot, or if I'm creating a struct like a dot data, and I give it a label, and the first thing is dot long, and then I_str. Why does that not detect that I'm trying to print a string?
I don't know, because you haven't given me all the rest of the context. You did do a bug submit, I think, right? Okay, so I'm still working my way through those. Thank you. I will get to it. Other questions? So actually, printing ints and strings is supposed to work now, and if it doesn't, well, we'll see. All right. Now, several people have asked, on that point, several people have asked me, or at least one person has asked me, am I going to make, am I going to have a pi make stir? Now, the reason that I didn't have that, there are twofold answer. First of all, the amount of code you have to write to call any function like that is about equivalent to the amount that you would have to write to lay out the string in memory, just with a bunch of declarations in the, say, the .data section. And two, the string is immutable, so in fact you can get away with doing that. And rather than create a new string every single time you execute, you evaluate a literal, you have just one constant string for that. So yes, the restriction of that in the current runtime to the runtime is in fact deliberate, because I was expecting that people would just decide, I'd like to have you lay out at least one object for yourselves besides function pointers, so you can see what a real object looks like in memory. Yeah, okay, questions? No? I continue to be amazed at your total familiarity with the details of this project. I am in awe. I don't know why I bother to teach this course. All right. Our dictionaries? Oh yes, I'm sorry. I was going to release them this morning, but in fact but then I got this spate of other runtime comments, and I thought probably 2 releases in one day might be pushing it. So the missing, yeah, right. So I forget what was missing at the time. The irritating thing with dictionary, there are some things that won't work quite the way they do in Python because it's just stupid or annoying. And for example, comparing dictionaries, is one dictionary less than or equal to another? It's not even well defined what that's supposed to mean in Python. Equal is, but not less than or equal. So that will be... There are some things that they do because they have to be nice and uniform and orthogonal and everything, and I just say, for our purposes, we don't need it. So, all right. Well, I'm going to because there's another problem set that will be coming out tonight or tomorrow. I thought the last problem set. I thought I'd start covering the material now. On Friday, I would like to spend some time talking about project issues, coding issues. So because there have been some requests for it, some of you would probably have preferred that I start earlier, but unfortunately, you see, I've been in this university too long, and I have learned that even despite my reputation, which I have spent years building up, people will wait until the last moment, which means the last 3 weeks, to do a project under me. So I do so I have to be careful in my timing. Meanwhile, the TAs will be meeting with you. I think I saw the announcement today, or was it yesterday, right? So, no? Yes? Yes, right. So they will also be helping you. Maybe some of you, if any of you get the religion, see the light, and suddenly become code style fanatics and would like to help, then I think I'll be able to find a place for you to as a reader or lab assistant in CS61B, which I'll be teaching next year. So I just advertisement. Okay. And if I like your code. All right. So the next topic is sort of, it's not one that's exercised in the project particularly, unfortunately. Nevertheless, it's a source of considerable interest. It has been for some time. And it's actually, we're actually sort of falling back, in effect, to static analysis, except that we're doing it well with a much different goal. So there is this topic called optimization. In the old days, say 1950, the Truman administration, you know, that kind of thing. The way that you programmed a computer, of course, was that you used, well, either assembly language or even something more primitive, perhaps. And it was sort of assumed that, well, if you can use this Fortran stuff if you want, but gosh, I mean, anything I write with in assembly language, my own hands, is going to be superior to anything you write with anything that stupid compiler generates. Well, this wasn't entirely true. In fact, Fortran was amazingly effective, and that it turns out that that's very important. It's important that in fact you can get a high-level language producing code that is comparable to what you could do by hand, or within spitting distance, you know, a reasonable integer factor of what you could do by hand, because that sort of enables, you know, it sort of encourages people to use high-level languages. And naturally, when things got really complicated, when we started having million-line programs in, or what is Windows these days? Do you know what Windows is? 50 million. At one point, I heard 50 million, but that was years ago. Lines of C code, but it declined a little. Oh, good for them. Yeah. So, but that's a lot of code. If you look at the usual productivity metrics, it's supposed to take to write that many lines of debugged code is supposed to, by some measures, is supposed to take 100,000 man-years or something. So it's and maybe it did, I don't know. So it's quite a bit, and in fact, writing the equivalent assembly language would be absolutely impossible. I mean, you just couldn't do it. So as a result, this becomes even more important. It becomes even more important, I think, to be able to or let's say more desirable to be able to have your cake and eat it too, to write in a high-level language and have it perform nicely. Okay, well, that said, you can't, despite the term optimization, you can't make optimal code in any practical way, but you can improve things. And I should also say, because we're engineers in this room, a lot of us, I should also say that sometimes, for most applications, good enough is good enough, right? So in fact, the fact that I could write it to make it go 10 times faster in hand-optimized assembly code or 100 times faster in hand-optimized assembly code does not matter for an application, for a program that runs for 100th of a second or something like this. And so there are always these trade-offs that we have to deal with. Okay, so let's for the moment just look at this problem of automatic improvement or automatic production of good code, of reasonably good code, and heuristics for doing that, heuristics and algorithms for doing that. So this is a list of a number of the classic optimizations. Well, I should say that static single assignment form is actually not an optimization. It's a enabling conversion, really. And we're going to do, first of all, so first as an overview, we'll just sort of look at these things so you know what we're talking about. All right, so terminology. A basic block. Basic block, I've already said what this is. It's a sequence of statements. It has no labels. You can't jump into the middle of it. You can only jump to the beginning. And you can't jump out of it except at the end. So it's statement that might have a side effect, statement that might have a side effect, statement that might have a side effect, test and branch, and maybe a branch at the end. Right? That's it. So that's the idea of what a basic block is, and that means that you can assume that all of the statements in the block get executed. Now, each time that you start. So if you start at the beginning, you will hit every statement in the block. That's the idea. Except, well, I mean, there will be some tests at the end. You might miss one or two of them, but the point is that you hit all of the statements that do anything, all of the assignments and so forth. So here's a basic block. And let's just think about this. So what are the improvements here? We notice, for example, that statement 3 is, since t is equal to 2 times x, if I add it to x, then I could just simply convert that whole statement, w gets t plus x, I could convert that to w gets 3 times x. And that leads to the question, well, gee, that would save me an instruction if I could get rid of that multiplication by 2. So what about it? Can I do that? Yeah?
Because something else can use t afterwards?
Right, so we don't know from this, we can't necessarily tell if we're going to use t, but obviously if we don't use t, if somehow we know that this is the only use of t, for example, t might be a compiler temporary. That's, if you remember how the sequences of 3 address code you might generate, if you had an expression in your high-level language that was something like t plus 2 times x, or 2 times x plus x, then it might very well generate code like this, and in which case you wouldn't reuse the t again. So it's a conditional thing. Sometimes you can do it, sometimes you can't. So all right, so that's what a basic block is. Now a control flow graph, this is another big concept, is basically a graph whose nodes are basic blocks. That's it. And that depicts control flow. That is, there's an edge from one block to another if there's a branch from the end of one block to the beginning of the other. It's always the end. It's always a branch from the end. It's always a branch to the beginning because that's the assumption about what a basic block is like. Okay, so now I should, the slight caveat here, I say the last instruction, it's conceivable, I think, if you've got you could conceivably translate a multi-way branch at the end into a couple of branches, but that's a detail. We'll treat that last branch as if it's a single instruction. Okay. So another way that you can follow an arrow in a block, it could be a branch. It could also be that you just come to the end of the first block, and the next block is supposed to be the next block in memory. So that you can depict that by having an arrow to that next block. Just explicitly, since even though there isn't a go-to statement, explicitly saying control is going to flow from this first block to the second block. So here's an example. Here's an example of a fall-through right here. So this one we have the complete code is this, and this. And therefore, when we finish with this block, we will fall through to that one, hence the arrow. So we can denote this as you see, we have these two squares here represent basic blocks. They follow the rules, and the arrows represent the possible flow of the passable control paths through this graph. Now, for a complete context, for a context-free grammar, for a complete control flow graph, yes, if anybody asks you what CFG means, you say, are we at the beginning of the course or the end of the course? Right, okay. So a complete control flow graph has an entry node and an exit node, a single entry and a single exit. And the or you can you can also do it. You can also have a bunch of exit nodes. It's convenient to conglomerate them all into one, however. Okay, so what we're going to so with that terminology in mind, we're going to attack the problem in stages. So first of all, what is it that we're trying to improve? Well, obviously execution time, that's the thing that people are mostly interested in. Code size, these days code size is somewhat less important because there's so much more memory lying around, and so you can you can be really profligate with it these days. But of course, if you're compiling for some small device, it's a different story. And also, code size, for a number of reasons, can be affected and affect execution time. So there's a trade-off here. Sometimes it's not a trade-off. Sometimes making a shorter program also means making a faster program. So sometimes these two things work together. You might, at a higher level, you might be compiling for a parallel language. And at a high level, you then have to worry about but by parallel language, I mean what we call a distributed parallel language, in which you've got different pieces of the program, of a single integrated program running on different machines. They communicate with each other by messages, and you would like to minimize that message traffic. Well, that's a form of optimization. It's a higher level form of optimization that I'm afraid we won't have time to deal with here. And then you might also want to optimize power and so forth, although, and people have looked at compiler technology for that. Although personally, I can't help thinking that one can get an awful lot of leverage by just proper design of the operating system for that one. But it's a possible target. Now, the idea here, optimization, is a form of program transformation. We're transforming the program into a better, quote, better program. But the bottom line is that we're supposed to preserve the semantics of the program. So that means that if your programming language, if your spec for the programming languages says, without any vagueness, that the program is supposed to do X, then the so-called optimized program should be doing X. Now you'll notice if you look in the specification of C, you'll see a lot of places where it just isn't said what something means. So, for example, if you overflow a signed integer, nothing says what happens. There's no statement about what happens if you do that. If you do if you do a right shift by a negative quantity or a left shift by a negative quantity, it's undefined what happens. All kinds of things are undefined, and one of the reasons for this lack of definition is that they wanted to be unspecific in places that didn't matter, because when you do that, you make it easier to generate fast code on a variety of architectures, and in some cases, you might also make optimization easier. So C, for example, does not specify the order in which you evaluate parameters, because sometimes you can get more mileage out of evaluating them backwards or forwards, as the case may be, and so this is left up to the compiler. Java took a different turn. Java basically specifies everything, so you know the order in which parameters are evaluated. You know exactly what happens if you overflow an arithmetic computation. All of that is defined, even down to the semantics of floating point, although they loosen that up a little bit. And because the goals there are different. The goals there are they're much more interested in portability, strong portability, and at least initially the need to generate absolutely optimal code. That took a somewhat less important. That was a less important point at the time. Of course, in the interim, Java compilers have come to produce pretty good code, at least certain compilers. Okay, so let's divide the space into different kinds of optimizations. We call an optimization local if it applies to a single basic block, if you apply the optimization to a basic block at a time. We call it global if it applies to a complete context, to a complete control, there I go again, complete control flow graph for a single procedure. All right? So this might seem strange. Global means, so local means single basic block or a single bunch of statements. Global means single function. What's beyond that? I mean, there's more than one function in a program. Well, you get the various names. For some reason, there wasn't a name. I had a student once who suggested galactic optimization, but we generally just call it interprocedural optimization or sometimes whole program optimization, meaning that you execute on the whole program. They didn't come up with a nice short adjective in that case. So these days, a lot of compilers do up through 2. 3 is, I say that very few do it. Actually, it's just that it's kind of limited. So, for example, one interprocedural optimization. Well, can you think of an interprocedural optimization right off the top of your head? You know about it already. You just don't think of it as an optimization. Right? What's an interprocedural optimization? You already know one. Yes, in the back there. That's right, inlining code. That's an interprocedural optimization. I speed things up by taking the body of this function, sticking it in here, and doing it directly and avoiding all the call and return overhead. Okay, so a lot of compilers for GCC will do that if you ask it nicely. In fact, it's often expected of it. Okay, so you'd think that interprocedural optimization would be desirable, and it perhaps is, although studies occasionally show and conference papers show rather disappointing results from various interprocedural optimizations quite often, but sometimes it's good. So compilers generally stop at 2, and already the problem is, and the problem is the cost of these optimizations. Some of these analyses require superlinear time, or linear time with a large constant or something like that. And if, in fact, you are in the mode of you're building and debugging a system, and you're running it over and over, you're going through the compile, debug, tests, script over and over again, really doesn't make a lot of sense to spend time on optimization, to spend a lot of time on optimization, number one. Number two, as you'll find if you haven't already, at high optimization levels, debugging becomes very difficult because the compiler has to communicate to the debugger somehow what it's done, all the transformations it's done to the code. Variables that appear in the program may have disappeared entirely because the compiler finds they aren't needed. But the programmer sitting there when his debugger asks, I wonder what the value of this variable is. And he asks the debugger, and since the variable isn't there, the debugger does some random thing. Like the nice ones tell you, I don't know, and the not so nice ones give you a random value, which looks totally ridiculous. So in general, you don't implement the fanciest optimizations, again, this is an engineering matter. We're trying to get the most bang for the buck. That's what you're trying to do. All right. Yes.
I was wondering, you know how there's all the conventions?
Yes.
Are there like compilers that like ignore the conventions so they can speed up the code?
Yeah, that happens sometimes. If the compiler is in complete control of some situation, it might do weird things. It might have special conventions for calling its own little tiny runtime routines that it uses for support of some things. I don't know offhand how often that happens, but it is certainly possible. And of course, that's a potential source of problems, I guess, in the finished product. All right, well, let's see. Why don't we, now that I'm about to get into specifics, why don't we just stop here and take a break? So, has anyone thought of some further project questions while you're sitting there in your mid-morning lecture doze or whatever? Okay, fine. I'll start again in a few minutes.
Do we need to create a symbol table, or it seems like we might be able to use your environments and schedules directly
To do what?
okay. Well, when we enter a function, we're thinking, okay, ask that function for its declaration, ask that declaration for its members, which I think returns.
Oh, you're talking about what should the compiler do?
Right.
Oh, okay.
So then the declaration can get its members to get its environment. We can ask the environment for its members, and then we can say, well, how many things are declared here?
Right.
And if it says 10, then great. We'll automatically decrement the stack pointer by 40, and create space for variable for those declarations.
Oh, I see. Yeah, you might want to. It's convenient to use the functions decl to accumulate information like that.
Functions.
Yeah, so you enter a function. The function has a declaration, right? So you can add some fields to that declaration in the compiler that keep track of, for example, how many local variables do I have, or something like that. And then you have a pass that goes through and fills in that information. And then when code generation happens, you're all ready to, you have all the information right there to generate the prologue and epilogue and so forth. So yeah, I mean, that works.
So that way we can avoid building like a separate symbol table and doing a whole
Well, if
pass.
you're starting from our framework, I don't see that you're going to need
I know.
very
I
much
don't know
more.
why anyone was ever trying to build one.
Yeah. No, it shouldn't. That should not be necessary, because I mean, the symbol. You've already had all of the symbols identified with a function and so forth. So yeah.
So then I guess we could just use the index in the vector for the members vector, the decl vector. We use a symbols index in that vector to determine its particular offset. Like index 1, we could say, okay, you're at offset 0.
You mean in the V tables?
So what?
In the V tables? In the dispatching tables? What, are you talking about local variables, methods? What?
Let's say it's a method. So that method will have an environment and it has a vector of members inside of it. And should we just like loop through all?
No, you're talking about local variables inside a member.
Yeah.
Oh, okay.
So when we
Yeah, you can do that. I mean, it's up to you. It doesn't. It's arbitrary what order you put local variables in.
right, but I mean that's a legit way of doing it. Like we can just use its index to determine its offset and not have to worry about it.
I think that works. I'm not sure what else. It's index in the member array. Wait a minute. Did functions have? My functions don't have a member array. You'll have to add one.
Functions don't, but the function has a declaration. I believe the declaration has its environment. Maybe I'm wrong. So I know function,
Not the way I did it anyway.
Okay, so how do you get at how do you get at that then? Because I know its body and the params.
You can find all of the declarations attached to a function by doing a scan of the function code, looking at all the identifiers and finding all the ones whose declarations say that the function contains it. Right? You can find the parameters by going to the parameter list, and there's the list of all the parameters right there.
I see.
Yeah. Or you can add some more stuff to the function decl. Nothing is sacred. You can,
I just wanted to make sure it wasn't crazy.
yeah.
How do we know what functions are available in the runtime? I was looking through the runtime, but I was trying to call some of the built-in calls, but
Everything that's extern is should be available to you.
okay, like I couldn't find get length in there, but it was
Get length.
Yeah, I tried calling it, but it wasn't found. It was in the runtime.
I'm not familiar with what get length is.
Or get _len.
That's not part of the runtime interface.
Oh, okay, that's probably why I couldn't find it.
I mean, what are you trying to do? Get the length of what?
I mean, just for truth values, I was going to get the length and compare it to
Oh,
0.
yeah, I should make an announcement about that. I put a comment in the runtime code, but yeah, to get truth values, call the function, the init function for bool. So py underscore py underscore init, py underscore bool underscore init, and so forth. And you pass it it doesn't matter what the first parameter is, pass it the second parameter, and then it will hand you back a bool. It's exactly what you want, actually. So, and thank you for reminding me. I had not announced that properly. Okay. Yeah. All right, let's get started again. Okay, so let's go through a sort of an overview of some classic local optimizations. Some of these will also turn out to be globalizable, but let's introduce the terminology now. So one obvious thing is that there are certain operations that you know about. I mean, you know the properties of some of these operators. So if you're in a statically typed language, so that you know that, for example, in these examples, x is an integer, then you can take advantage of that by converting these statements, as you see over there. So you know that multiplication by 0 gives you 0. You know that squaring squares. You can a multiplication by a power of 2 is a shift. Those optimizations are less important these days, what with the improvements in hardware, but sometimes it's kind of interesting. Or then you can have something like multiplication by things that aren't powers of 2 but are easily representable, as you see there. So times 15 is the same as times the quantity 16 minus 1, which is the same as multiplying x by 16 and then subtracting x. So these are all tricks that people have done in the past. Unfortunately, not so interesting today, except maybe when you're talking about floating point, they may have some interest. The problem with floating point, unfortunately, is that many of these rules, or some of these rules, don't really work too well with floating point. For example, with IEEE floating point, a negative number times 0 gives you negative 0, which is not the same as 0 in a very subtle way. And so you have to be a little bit careful with floating point. Let's put it this way. Every time I think about doing some optimization involving floating point, Professor Kahn yells at me, so I don't do that anymore. All right. Another local optimization is constant folding. Now, this refers to computing. Refers to computing the value of constant expressions. It's really, I guess, a form of algebraic manipulation, in effect, but it becomes kind of useful. So x gets 2 plus 2. Now, you might say, why would anyone write 2 plus 2 in a program? Why would that ever occur in a program? Why would any expression like that occur? Why would it? You're programmers. Why would such a thing? Is that what you do? You write programs? Instead of saying x equals 4, you say, x equals 12 divided by 3. I mean, is that... Yeah.
Maybe you can inadvertently declare two constant integers where the file you added this to.
Okay, would you, how about something that you do deliberately? Yeah.
Some optimization elsewhere that has some constant value.
Yeah, you never know what will happen. The actual text of this might be something like, my original text might have been x equals y gets y plus 2. And y was set elsewhere. But, okay, but even, you'd think you could avoid even that. Why not? Yeah. That's right. You might have symbolic constants. It just might be better, it might read better if you could represent things symbolically, or if you could use macros that expand in peculiar ways, but that are clear to read, but that in fact have expansions that produce constants. So for all of these reasons, you don't have to write something stupid to have one of the intermediate steps look kind of stupid. And it's good for the compiler to be able to clean this up. Now, this second one here, the second example, is particularly interesting because it's a way in which there's an optimization that doesn't involve just arithmetic, but also something more complicated, a jump. So this is the case if 2 is less than 0, jump L. Well, you know that, of course, that will never be executed. You can tell at compile time, so you can eliminate the statement entirely. And similarly, if 2 greater than 0, jump L, you would know that you should just turn it into a jump to L. There's nothing weird going on here. So I asked this question about when might it be dangerous? When might it be dangerous? Or let's say surprising, maybe. Any thoughts? Might something weird happen? All right, let me ask a leading question. All right, what?
The remaining addresses, code addresses, might be shifted now by 4, say if the instruction was taken out. So all of your offsets, you're saying if it was replaced with no offset?
Yeah. Well, now wait. I see where you're coming from. It's not as if we go into the final code and apply these optimizations willy-nilly. We are modifying the program before actually generating final code for it. So the kind of problem that you're thinking about doesn't necessarily happen. It's not as if I'm doing this in the assembly language, and which would indeed cause havoc if I'm not careful. Yeah, but there are other things. So what is an optimization? Yes.
I was going to say, some languages like Python lets you redeclare the value of true. So if true jump L, and you redeclare it false.
Yes, Python 3 doesn't let you do that. Yeah, well, of course, in those cases, it would never be right to think. And most of these optimizations don't apply to full Python. I mean, it's just because but they don't apply to full Python because what is the cardinal rule for optimization? Optimization is supposed to preserve what? Correctness. Well, yeah, but whoever gives the compiler a correct program, yeah, right? Correctness meaning the meaning of the program. So if the program was wrong before, it should continue to be wrong. And, well, no, not necessarily. But if it was right before, it should continue to be right. What you'll sometimes see is somebody writing, for example, if x divided by 0 equals blah, 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 deliberately, or say y gets x divided by 0, deliberately intending that this cause an exception. There are various reasons for that, but of course, if the compiler says, "Oh, this is going to cause an exception," I will. Well, there are two things that can happen. The compiler say, "This is going to cause an exception, so I'm just going to replace it with a jump to the exception handler. Or it could say, this is going to cause an exception, and my language has been written, as some are actually, has been written to say that exceptions are not guaranteed to happen if the compiler can convince itself that it's harmless to do away with them or something like that. And so funny things happen. This usually it's only in pathological cases that this really comes up, I think, having to do with people testing their programs, their compiler in various ways. Okay, so here's an example of a global optimization now. Although actually you can also apply it on a given basic, well, you could apply it to a basic block, except that that's usually kind of trivial. So it's possible that as a result of various optimizations, as for example this one right here, this one, it's possible that because of applying those optimizations, you find that basic blocks become unreachable. All right. So what you can do in those cases is those basic blocks are not necessary. You could just throw them out entirely. We say that code is unreachable or dead, and we throw those statements out. Dead has another specific meaning, but we say it's unreachable, so you can throw it out. All right, so that's nice. All right, so those are a few examples. Those are a few examples of optimizations. Now, in order to talk about some of the rest of them, I'm going to take a little side trip here and look at a particular rewrite that we do. It's known as putting the program into static single assignment form. All right, so it turns out that there are certain canonicalization is not the right term, but it's something like that. Certain standardizations, if you will, of the code that are sometimes useful for either implementing or describing optimizations, and this is one of them. So take a look at the code on the left and right. On the code on the left, I'm reusing I reassign to the variable x, to the local variable x, a couple of times. And in the code on the right, we change that. So we change that so that every single time we assign to something, the very first thing I do is I reassign to A, which presumably was assigned somewhere above me in the code. I can also keep introducing new temporary variables so that every single assignment is an assignment to a new variable. So I have no assignments, I have no cases in which I assign from the same variable twice. When I get that, when I assign to X, when I assign to A, since there's already an A around, I will instead introduce a new temporary variable, A1, which I will use subsequently when I have to refer to the new value of A. So in principle, the new value of A, A1, and the old value of A are both still around, and available for my use later on in the code. Likewise, when I assign to X, I can introduce a new variable, X1, so that I can refer to the previous value of X and the current value of X. And in each of these cases, this has certain interesting properties, one of which is that for every variable in the transformed program, there is exactly one assignment. You can point to one statement in the program that is its source, or the term that we use is definition, although that's kind of confusing. And for describing certain optimizations or certain optimization techniques, that's kind of convenient. Now, you might very well ask, I can see that this is going to cause some problems, as, for example, when I have a code with two branches coming in, and I assign to a variable in both of them? How can I have just one assignment? And that's an interesting question. Keep that thought until we come to the answer, which is kind of weird. All right, so let's take a look at another classical optimization. No, let's not. Let's end the class because it's noon. All right, so I will leave things on that cliffhanger, and we'll take it up again on Friday. Please bring your project questions. If you have some questions about structure and so forth of the project, how you should do things, Friday would be a good time to have them ready.